A question leans forward like a compass needle. If everything turns, why does stillness feel so complete? The world rotates beneath midnight cloud and afternoon weather, and the illusion of rest endures. Oceans, mountains, and cities share a persistent glide, so even that it dissolves into habit. The planet completes one sidereal turn each day, the surface near the equator moving at about 1,037 miles per hour. And yet a quiet hand does not tremble. The explanation begins with inertia and continues with shared frames of motion. When motion is uniform and unbroken, no internal signal announces it. A body animated by the same smooth rotation as the ground beneath has nothing to compare against, so motion becomes a background truth rather than a felt event. In ordinary experience, acceleration writes itself into the body with clarity. The inner ear answers instantly to a start, a stop, or a curve, but it does not report a long, steady ride. A train gliding along a straight track produces no sense of speed until a turn arrives and the difference speaks. So it is with the planet. The spin is ancient, and even a river of motion that began before language and settled into the background of each day. Without a change in speed or direction, the senses rest, and rest masquerades as stillness. Physics names this circumstance inertial motion. In such a frame, the simplest laws keep their form. A cup on a table does not slide because the table, the cup, and the air around them already travel together on the same broad carousel. The atmosphere participates, so there is no constant gale to announce the turning. Only when gradients emerge does motion step out of hiding, a gust crossing a front, a current meeting a shore, a wheel easing into a stop. Yet the calm can be measured. A pendulum hung to swing freely traces the turning of the ground beneath it. The Foucault pendulum needs no star chart to make its case. The plane of its swing keeps faith with distant space, while the floor, the hall, and the patient observer imperceptibly rotate. Over hours, a slow procession of markers topples in a circle, and the invisible becomes literal. Similar proofs live in star trails captured by long exposures and in the steady march of shadows across meridian lines built into observatory floors where the day's rotation becomes geometry written in light. Shared motion reaches outward. The planet orbits its star at about 67,000 miles per hour, and the star drifts around the galactic center at roughly 514,000 miles per hour, yet perception remains sheltered by the same principle. The biosphere, the atmosphere, and the crust travel together carrying books and instruments and sleeping rooms as passengers within a larger frame. At each scale, uniform motion becomes the neutral background and only changes are felt. Relativity deepens the idea without disturbing its calm. There is no absolute rest, only rest with respect to something else. Choose the planet and a figure at a window appears still. Choose the star, and that same figure speeds along an ellipse. Choose the galactic center, and the same body rides a grand spiral. The laws remain consistent across those choices, and sensation remains quiet because the body experiences no abrupt demand to reorient. There is also a biology of quiet. The vestibular system is tuned to protect balance during walking, climbing, and turning, not to summarize planetary statistics. It answers to acceleration rather than to the silent sweep of a continent beneath the night sky. The nervous system filters steady signals so that change can command attention. An animal that ignored sudden shifts but constantly reported uniform motion would fare poorly. Evolution favors the opposite. The result is a silence that is not ignorance but efficiency. The stillness is not perfect. Subtle traces accumulate where careful tools attend to them. High-precision clocks reveal tiny differences in tick rate between the equator and the poles, an interplay of speed and gravity that modern physics predicts and engineers correct in navigation systems. Tidal rhythms slip across coasts as a reminder that the spin is linked to the steady pull of the nearby moon. Jet streams curve under the planet's rotation and write spirals in cloud that orbiting satellites can follow for days. Beneath the quiet of daily life, instruments keep a ledger of motion. The heritage of the spin reaches back to origin. A cloud of gas and dust collapses under gravity, and angular momentum, once diffuse, grows obvious as the cloud shrinks. Conservation of that angular momentum imprints rotation on the newborn star and on the disk of matter that gathers into planets. The present cycle of day and night is therefore a fossil record of an earlier, greater turning preserved not in rock but in the length of each rotation. The serenity felt by living things today is built upon that inheritance. Perception accepts this heritage and calls it normal. A hillside, a street, a room all appear as restful platforms, yet each rests only within its own moving frame. The calm at any level is a conditional truth, and the condition is sameness of motion. When sameness breaks, sensation wakes. A seismic wave rattles a shelf, a sudden stop nudges a traveler forward, a gust leans trees toward neighboring air. Every such event is a local reminder that the broader motion continues even when unfelt. The idea of stillness, then, is not an error but an agreement. Matter agrees to move together so perfectly that difference vanishes. Instruments built to disagree with the body recover the hidden rotation and translate it into numbers, graphs, and faint arcs of light. Museums set pendulums to swing in quiet foyers where the floor will circle beneath them for hours. Observatories align stone and shadow so the day's advance becomes a measured line. Laboratories compare clocks separated in latitude and gently extract the tiny consequences of a turning world. A scene at dawn completes the thought. A bird settles on a railing as sunlight climbs a wall. The railing, the bird, and the wall traverse space together in coupled motion, and awareness reports only warmth, light, and the small rustle of feathers. Beneath that everyday calm, the planet turns, the orbit continues, and the galaxy carries both along. The quiet feels honest because the differences are small, and the differences are small because the motions are shared. Balance is not absence, it is harmony among many movements. At the center of that harmony waits a deeper question that the next inquiry will open. If stillness is an agreement among motions, where did the agreement begin, and what first set the turning in place? A quiet instrument enters, as witness a weight on a long wire released to swing, deciding with patience whether the floor beneath truly turns. In the middle of the 19th century, a careful experiment takes its place in a hall. A slender wire stretches from a high dome, and at its end a heavy bob begins a slow, unwavering arc. The plane of that arc remains faithful to distant space while the building, the ground, and the continent move. Hours pass. Around the pendulum, a circle of pegs waits. One by one, at a rate set not by hands but by latitude, the pegs fall. The demonstration is almost ascetic in its simplicity. No gears declare themselves, no engine hums. A single line reveals a planet's rotation with nothing more than time and gravity. The principle rests on independence. The pendulum, once set in motion, prefers to keep its plane of swing. The Earth, turning steadily, prefers to keep its spin. The difference between these preferences becomes visible as a slow precession. At the poles, that precession completes a full circle in one day. At the equator, it pauses entirely, the plane of swing keeping pace with the ground beneath. Between those extremes, the rate follows a quiet geometry linked to latitude, a relationship that observatories and museums demonstrate with calm precision. Builders make the instrument honest. The wire must be long and free of twist. The bob must be heavy and shaped to slice cleanly through air. Sometimes a small electric impulse at the end of each swing restores a bit of energy lost to friction, not to force the path, but to preserve it. Visitors return at midday and again near evening to find a new peg toppled, a silent ledger of planetary motion. The pendulum does not dramatize. It simply persists until the room itself seems to admit that it is the thing in motion. This clarity extends outdoors. Point a camera at the northern sky and hold the shutter open long enough, and starlight draws circles around a fixed point. The photograph records what the body does not feel. Shadows cross meridian lines set into stone floors, and the day's arc becomes a measured stripe of light. In both cases, as with the pendulum, a local frame yields to a larger one, and the eye witnesses a difference that nerves alone do not report. Engineers carry the idea into instruments that do not need a dome. A mechanical gyroscope spins a rotor and resists any effort to tip its axis. Left alone, it preserves direction the way a pendulum preserves a plane. The same sky that a long exposure reveals becomes a reference for a spinning wheel sealed inside a compass. Later, light itself becomes a rotor in a ring of mirrors. Two beams march in opposite directions around a closed path. When the device rotates, the path length for one beam grows while the other shrinks. The interference between them shows the rate of turning. In ships and aircraft, these ring instruments quietly report the same truth as the pendulum, peg by peg, hour by hour, mile by mile. Even fluid remembers. In wide basins of water, slowly drain through a centered hole, residual swirls and local drafts dominate, and the drain may spin this way or that. But under careful conditions with disturbances allowed to settle for long hours, a preference appears that matches the planet's turning. The effect is subtle and easily spoiled, a reminder that nature writes her signatures in mixtures of strong and faint lines, and that patience is the reagent that reveals the faintest. The pendulum also introduces a lesson about place. The rate of its twist is not universal, it belongs to where it hangs. In that dependence on latitude lies the elegance of the argument. A hidden rotation could be denied if the effect were the same everywhere. It is not. The arc turns quickly in polar halls, slowly in temperate ones, and not at all where the equator passes. The floor's quiet confession gains strength through these differences across the globe. The experiment suggests a discipline of looking. Instruments are modest agreements with nature, build with care, remove disturbances, and allow time to speak. The reward is a line of evidence so simple that it becomes beautiful. A child can watch a single peg fall and begin to trust that the earth turns. A mathematician can write the relation in symbols and trust the same turning from a proof. A navigator can keep a course by a spinning wheel sealed from wind and waves. Three paths meet in a single motion that does not need to be felt to be real. Silence serves the demonstration. The pendulum's environment is a museum atrium, a library, well, a train station with a dome and a circle of daylight at its crown. The thin wire trembles when a door opens, then calms. The crowd breaks and reforms. The bob continues. In that continuity, the instrument becomes a clock of rotation rather than of hours. Where ordinary clocks divide a day into equal intervals, the pendulum translates the same day into the gentle march of a turning earth. It converts an invisible background into visible change. The experiment also connects eras. A swinging weight in a hall echoes the ancient practice of watching shadows, which itself echoes the older habit of marking seasons by the rise of familiar stars just before dawn. Each method refines attention from broad signs to fine measures, but all aim at the same question: how does this world move? The pendulum answers with local certainty and invites larger thoughts. If the floor turns beneath an instrument in a city, then the city turns beneath a sky, and the sky itself participates in motions that are nested and grand. That invitation opens the path ahead. The next idea asks what the pendulum quietly implies but does not display. The instrument proves rotation at one place, but the world belongs to a chain of motions that do not end with a single spin. A planet circles a star orbits a galactic center, and that center drifts within a structure stitched by gravity. Frames overlap, and rest becomes a choice of vantage rather than a final category. The pendulum has done its patient work. It has taught how to see the difference between a local frame and a larger one. The inquiry now widens to follow orbits within orbits, and to ask how perception, measurement, and law keep their poise as the frames expand. A nested map unfolds. A world circles a star, while the star circles the center, and the center itself drifts through wider structure, so that rest becomes a matter of which circle the mind chooses to hold still. Daylight and darkness arrive because the planet turns, but seasons speak of another motion, the long path around the parent star. The orbit is nearly an ellipse, so the planet moves a little faster when nearer to the star and a little slower when farther away. Yet the alternation of light and climate feels steady because overlapping cycles blend into habit. The year is only the local name for one ring in a larger chain. Each orbit carries smaller motions inside it. The planet and its moon travel not as a bead in a string, but as partners around a shared center of mass that lies beneath the ocean and within the crust. This shifting center persuades tides to advance and retreat, nudges the rotation by tiny amounts, and invites careful instruments to notice how the ground swells and settles by quiet centimeters with each passage. The daily calm holds yet a ledger of motion, accumulates in coastal timing, in satellite paths, and in the slow arithmetic of lengthening days. The star obeys the same logic at a grander scale. It holds the planets in slender ellipses, yet also answers a deeper pull toward a galactic center threaded with old stars' cool dust and an unseen halo. The stellar neighborhood participates in differential rotation where inner lanes complete their circuit sooner than outer ones. A single cloud at one radius lags another at a different radius, and spiral arms arise not as rigid structures, but as patterns that pass through the disk-gathering material and letting it go like waves moving through a field of grain. Beyond the disk, the wider group exerts its claims. The home galaxy shares space with companions in a loose cluster bound by gravity. Another large spiral approaches across that shared emptiness, and their future meeting already writes faint tides into the outskirts of each system. Within this community, space itself expands, stretching the farthest distances, but binding winds on local scales. Islands of matter keep their orbits, while the larger ocean quietly grows between remote lights. Against this backdrop, a different kind of reference waits in ancient radiation. The sky holds a faint bath of microwaves that arrives from every direction, the cooled echo of an early hot universe. When motion carries an observer one way through this sea, the light ahead appears slightly warmer and the light behind slightly cooler. This soft dipole mark reveals a speed with respect to the oldest light and provides a peculiar compass. It does not restore absolute rest, but it allows a statement about how swiftly the local island moves through the wider deep. Past centuries wrestled with frames before this compass existed. Epicycles once multiplied to match the wandering paths of planets on the dome of night because the Earth was assumed to be still. Then a different frame was chosen, and the wandering became simple. Later, the preference for no special frame matured into a principle. The laws take the same form in any smoothly moving laboratory. Experiments built to detect a universal wind in space returned no drift, and light kept the same measured pace no matter the direction chosen. Even without delicate devices, nature leaves signs of orbital motion that patient observers can collect with a telescope. When the planet circles a star, the direction to a distant sun shifts slightly from month to month. Starlight enters the instrument at a tiny angle, and the apparent position draws a small oval over the year. This aberration of starlight confirms that the world does not simply rotate. It also sweeps forward. The effect does not disturb daily life, yet it is firm enough to stand as a quiet proof written in angles. Within the same sweep, the star itself betrays the pull of orbiting worlds. As a planet tugs, the star wobbles a little, drawing spectral lines back and forth by small velocities that careful spectroscopy can resolve. Or the planet crosses the stellar face and a slow, precise dimming repeats. These signals reveal families of orbits around other suns, where the same hierarchy repeats with different balances of distance, tilt, and time. Orbits within orbits are not unique to home, they are the common grammar of systems everywhere. In daily life, these nested frames shape subtle things. Air currents curve because the ground slides beneath them. Ocean gyres close loops because the planet turns inside its orbital path. Long flights shorten or lengthen with the direction of winds drawn by that curvature. Clocks in fast paths and clocks in slow paths part ways by tiny amounts, differences the body cannot feel but instruments must respect. Navigation works only because engineers meet the world on its own terms and correct for layered motion folded into every signal. Choose a frame and quiet returns. Stand with the turning ground and declare the room at rest. Ride the planet around the star and the seasons even out. Follow the star around the galactic center, and a greater year begins long beyond any calendar. Each choice is honest for describing local events, and mathematics ties them together so predictions agree when translated with care. The seeming paradox that everything moves and yet rests still exists, dissolves into a language of transformations between frames, yet traces hint that the hierarchy may continue beyond the familiar. Maps of the oldest light show patterns that are nearly uniform but not perfectly so. Alignments stretch suspiciously far, and researchers debate whether those lines are born of instrument of chance or of a whisper of a preferred direction on the largest scales. The idea does not claim a cosmic axle with obvious spokes, only that the initial conditions may have carried a small bias, a tilt echoed faintly across structure today. If such a bias exists, its influence would be modest, a seed, rather than a command, but a seed can matter when gravity and time have long to work. Spiral arms might inherit a slight tendency, or the statistics of rotation in large samples might lean by a hair. The question invites care because data are shy and alignment loves coincidence. Still, the possibility keeps attention open toward origins and toward the first moments when motion took a definite shape. The nested map therefore points in two directions at once. Outward toward larger frames where local notions of rest dissolve into wider drifts. Inward toward the earliest interval when the first circles began perhaps not as clean rings but as fluctuations stretched across a newborn cosmos. The pendulum and the star trail prove local turning. The aberration and the microwave dipole reveal orbital and galactic drift. What remains is to approach the first turn itself, the quiet beginning that taught every later circle how to move. A first turn hides in the earliest light before stars, before atoms. Motion is already choosing what kind of universe will be allowed to take shape. The trail to that beginning runs backward through layered signals. Starlight gives way to the afterglow of a hot origin, a nearly uniform sea of microwaves arriving from every direction. Tiny differences in temperature sprinkled across that sea, roughly 1 part in 100,000 mark places, where density stands a little higher or lower. Those faint patches become scaffolding for later structure because gravity rewards even the smallest head start. The map of these irregularities is not a decorative pattern, it is a fossil record of initial conditions written as softly as possible and still able to endure. Earlier still, the narrative turns to an episode of sudden enlargement. Space itself expands with extraordinary haste, stretching quantum jitters to astronomical scale. In a laboratory, such jitters remain hidden, but when distances balloon, their imprint is written across the sky as the delicate grain now preserved in ancient light. This episode is inferred rather than directly watched, yet it resolves several tensions at once. It explains why far regions look similar, why the ancient glow is nearly even yet not perfectly so, and why the small differences match a statistical script that gravity can understand. In this telling, the first turn is not a wheel set spinning like a planet. It is a permission written into the earliest conditions for small curls to coexist with waves. As space swells, any primordial whirl is diluted to near silence, but near silence is not a ban. Later, when matter cools and can clump, gravity amplifies the leftover tendencies. Neighboring regions tug unevenly and tides raise torques that twist infalling clouds. Rotation then emerges as the consequence of 3 lines in one sentence: initial irregularities, rapid enlargement, and long gravity working with time. Evidence meets this picture from several directions. The microwave sea carries not only temperature differences but also a subtle polarization, a memory from the era when free electrons last scattered light. Within that polarization, gentle swirls can act as fossils of curls in the gravitational field. Instruments on high plateaus and at polar ice joined by satellites above the air have searched for these swirls with patient campaigns. The discussion remains careful as it should, but the method is clear. Seek a curling pattern that ordinary density waves cannot easily mimic and listen for the faint rotational accent of the first moments. On the scale of galaxies and filaments, a complementary mechanism adds spin. As a dark matter halo assembles, it does not collapse symmetrically. The surrounding mass pulls more strongly from some directions than others and imparts a slow twist. This tidal torque picture, tested in numerical experiments that evolve vast swarms of particles from early fluctuations, produces families of disks and bulges whose rotation arises without prescription. The match to surveys is not perfect in every detail, yet the broad agreement is steady spins grow, where asymmetries in gravity are given enough time to talk to each other. Hints of a preferred direction on the widest scales have appeared and receded. Alignments among the lowest patterns in the ancient map, curious variations in strength from one wide patch of sky to another, and long axes proposed across data sets have drawn attention more than once. Teams have revisited calibrations, masked foregrounds, compared instruments, and asked whether chance alone can compose such coincidences. Most claims soften under scrutiny. The simpler picture of an almost isotropic beginning continues to stand with any large global rotation pressed below very small limits. A more certain statement concerns motion with respect to the oldest light. The microwave sea is slightly warmer in one direction and cooler in the opposite. This clean dipole arises because the local collection of galaxies moves through the bath. From that contrast, a speed and a heading can be read, placing the home system within a broader flow. The measurement repeats a lesson learned from pendulums and gyroscopes alike. There is no absolute rest, only frames within which the same laws keep their shape. Laboratories echo the early script in miniature. In ultra-cold gases, interference fringes appear when expanding atom clouds overlap, a small example of quantum ripples becoming visible when a system is made to grow. In superfluids, arrays of vortices crystallize when a gentle rotation is applied, showing how a nearly featureless state organizes into orderly whirlpools. These analogues are not the cosmos, yet they rhyme with its method, begin with tiny variations, change the scale quickly, and allow conservation to do the rest. Across great distances, the James Webb Space Telescope measures the motions of gas in very young galaxies whose light has been traveling for more than 13 billion years. Some already show settled rotation and narrow disks. Large ground observatories add to this with spectra that resolve velocity across each small face. The presence of such order so early implies that the bridge from initial ripples to coherent spin is efficient. Gravity wastes little time turning a small bias into a steady whirl when fuel is abundant and cooling is kind. The first turn is therefore not a single pivot in time. It is a field of permissions set at the beginning. Fluctuations allowed, polarization allowed, slight curls allowed, rapid enlargement allowed. From that field, later matter learns to rotate. Parts of the evidence are argued by statistics rather than spectacle, while other parts are nailed down by repeated measurement. Taken together, they sketch a consistent path from ancient light to present motion. Uncertainties keep the inquiry alive. Whether the entire cosmos ever held a net rotation beyond very small bounds remains a question constrained by limits rather than detections. Whether subtle anomalies in the ancient map point to new physics, or to the clever persistence of dust and instrument continues to be tested with deeper surveys. Forthcoming observatories that map weak lensing over enormous areas and missions that listen for far mergers through waves in space-time will refine the history of how angular momentum grows across the web of structure. A final image anchors the idea. Picture the first light as a calm lake with ripples no taller than 1 part in 100,000. As the water cools, the ripples gather floating leaves. Then the leaves draw slender streams. The streams meet and form eddies, and in each eddy the spin becomes clear. The lake does not begin as a whirlpool, yet the possibility of whirlpools is present from the start. In that sense, the earliest light already contains the first turn, not as a visible wheel, but as a promise that motion will take shape wherever gravity can find even the faintest imbalance. In the cold heart of a dark cloud, a spin no wider than a whisper chooses the architecture of future suns and worlds. A giant molecular cloud drifts where starlight is thin. Temperatures fall toward the quiet of deep night, and dust grains wear mantles of ice. Within this dim breadth, gravity gathers a clump. The clump is not perfectly still, not perfectly round, not perfectly balanced. Turbulent eddies pass momentum back and forth until one patch wins a little more mass than its neighbors and begins to fall inward. As the patch shrinks, a small initial turn becomes a stronger one because angular momentum is conserved. A faint rotation that once took many lifetimes to complete now quickens with each mile of collapse, and the center brightens. The forming star does not swallow all the turning. A disk spreads out around the newborn light, a broad and thin structure where gas and grains orbit in orderly lanes. In that disk, the rotation is not arbitrary. Speeds fall with distance in a way set by gravity, so that inner rings outpace outer ones, and the whole pattern stays stable for long periods. The disk is a ledger that keeps track of angular momentum the collapsing core could not carry inward. To solve this balance, matter moves fields thread the gas, and the system invents a way to shed excess spin without losing its shape. Magnetic fields answer that need. Ionized gas couples to magnetic lines that wind with the rotation and launch narrow outflows. Twin jets erupt along the spin axis and carry momentum away from the center. The core can then continue to contract while the disk spreads, and the forming star avoids the paradox of too much turning to become a star at all. Herbig-Haro shock fronts glow where those jets meet slower gas, writing the story of angular momentum export and knots of light that drift over years and decades. Observatories anchor this narrative in images and spectra. The Hubble Space Telescope traces jets as pencil lines carved across dark nurseries. The Very Large Telescope resolves scattered light from the surfaces of disks and measures the curve of velocity across them. The Atacama Large Millimeter Array sees rings and gaps in cold dust with such clarity that the lanes appear like grooves pressed into a record. Around a young object in torus concentric rings stand out as if placed by a deliberate hand, yet they arise from pressure ridges where drifting pebbles collect. The James Webb Space Telescope reaches deeper into the infrared and watches warm molecules spin and vibrate, revealing how gas moves inwards while some material escapes along magnetic routes. Within the disk, dust grains, coated with ice, stick in gentle collisions. Millimeter clumps become centimeter pebbles, then stones, then embryos of worlds. The flow of gas past these solids produces a drag that can concentrate material into dense filaments. Their gravity takes hold again, and the first kilometer bodies assemble. The rotation of the disk sets the spin direction of these building blocks. Collisions transfer and trade angular momentum until a family of planets emerges with shared motion but distinct days. Far from the star, a cold boundary marks where water can freeze in sunlight. Outside that snow line, ice helps grains stick, and giants can form cores quickly. Inside rock and metalwork more slowly, and smaller worlds take shape. The earliest solids remember the tempo of this birth. Primitive meteorites preserve cooled droplets and fragments, fused in short heating events, a record of shocks and magnetic bursts that pass through the disk. Their minerals tell of temperatures and pressures that rose and fell as the disk turned and evolved. Some carry magnetic imprints, a fossilized account of fields strong enough to break rotation and launch winds. In these stones, rotation is not an abstract parameter. It is a cause that leaves textures small enough to hold in a hand. The rotation does not end at the star. Young suns spin rapidly, then slow as magnetic winds reach into their disks and link star to gas. The tether drains angular momentum from the stellar surface and gives it to the surrounding flow, a transaction that allows the star to settle into a calmer pace. The system acts as a governor that keeps rotation within workable bounds. Where disks are massive or companions, close tides and torques complicate the accounting, and binary stars share or exchange spin in long negotiations that unfold over millions of years. Wide surveys show that disks often tilt relative to stellar equators, and that neighboring disks can point in different directions within the same nursery. Clouds do not collapse symmetrically, and nearby gravity can twist paths as they form. Yet across this variety, two themes persist. Rotation emerges easily when asymmetries in time are present, and systems find channels to move excess angular momentum outward. Jets, winds, magnetic braking spiral waves, and interactions all carry the same message in different dialects. Some disks reveal lanes that look like the handwriting of newborn planets. A planet carves a gap and raises a wave that propagates around the ring. Gas streams across the gap along narrow bridges while dust piles at the edges. These structures have been caught in the act by the Atacama Large Millimeter Array and by high contrast imagers on large telescopes. The features rotate with periods of years, and when revisited they have moved, proving that the patterns are not fixed decorations, but living consequences of orbiting masses. As planets finish forming, their individual spins carry traces of local history. A world built from many glancing blows may tilt or turn backward. A close encounter can lengthen a day or trade angular momentum into an obliquity that seasons will later amplify. Moons enlarge the dance, locking some rotations and stabilizing others. The assortment of day lengths across known worlds is not random, but the end of a long chain of exchanges that began when a quiet patch in a dark cloud first began to turn. Starbirth therefore acts as a forge that shapes rotation across many scales at once, from a whisper of spin in a cold core to the lanes of a bright disk to the gyroscopes of finished worlds. The same conservation works with different tools. Observatories provide snapshots with enough resolution to assemble a moving picture, and that picture keeps returning to the same idea. Spin is both inheritance and outcome, passed forward from a first imbalance and refined by fields, flows, and time. All of this prepares the ground for what the next inquiry will require. A spinning world does more than tally the history of its birth. It sets a cadence for light and dark, for winds and currents, for chemistry and growth. Rotation becomes climate's metronome and biology's clock. Having followed how seeds of spin take root in star nurseries, the path now turns to the surface of a living planet and asks how a day born in a cloud becomes the quiet architecture of life. A planet's day is not a simple spin, it is a hidden engine that writes weather, time, and memory into everything that lives, and the smallest change would redraw the world. The turning of the world divides light and dark and spreads heat unevenly across latitudes. Near the equator, sunlight arrives steeply, while toward the poles it slants and softens. Rotation gathers this contrast into motion. Warm air rises in broad belts, cool air descends in others, and long ribbons of wind circle the globe. The day's cadence keeps these cells in balance so that deserts, forests, and oceans receive a pattern rather than a chaos of energy. Without the spin, heating would pool on one face and deep cold would bury the other. With the spin, the planet breathes. Rotation does not move air in straight lines. As the ground slides eastward, moving air curves. This quiet curvature shapes trade winds that cross oceans, mid-latitude jets that guide storms, and polar flows that fold cold air into arcs. Ocean water answers with its own spirals. Surface currents close wide gyres, western boundaries race narrow and swift, and upwelling lifts cold nutrient-rich water where winds pull surface layers aside. The day's steady pace gathers the sun's uneven gift and carries it outward, turning sunlight into swells, clouds, and rain. Weather inherits this choreography. Storms organize when warm seas supply vapor and rotation supplies a frame. Near the equator where the day's turning is felt, but the deflecting strength as small clouds grow tall and march in lines. Farther poleward the deflection strengthens and cyclones trace graceful spirals that satellites watch form and fade. Jet streams meander as long waves, and their curves decide whether a continent basks in gentle air or braces for cold, whether rains linger or hurry on. These patterns are not random pictures on satellite screens. They are the handwriting of rotation on a living atmosphere. Life arranges itself to that handwriting. In the sea, countless small creatures rise toward the surface at dusk and sink again at dawn, a vertical commute that moves more mass each night than all land animals together. Along coasts, intertidal communities time feeding and shelter to cycles set by the spin of the planet and the orbit of its moon, counting days not by clocks but by the rhythm of water climbing and falling on rock. In forests, leaves open and twist with the sun, then fold in darkness. In grasslands, flowers time nectar and color to hours that pollinators learn. Within bodies, molecular gears keep near 24-hour beat-turning gene activity on and off so that energy, repair, and rest arrive in the right order. The length of day sets the stability of seasons. A turning that completes in roughly 24 hours keeps the surface from overheating under a noon that lasts too long, or from freezing under a night that will not end. The planet turns before extremes can take hold, and the ocean with its slow memory of heat joins the rotation to smooth the cycle further. The result is not uniform comfort, but a range within which rivers can flow, soils can build, and organisms can specialize without constant catastrophe. The engine shows its reach by contrast with other worlds. Jupiter spins in about 10 hours. The strong deflection divides its atmosphere into bands and jets, piling storms into long-lived vortices that astronomers watch for generations. Venus rotates backward and very slowly, taking about 243 days to turn once. Its thick air super-rotates, racing around the planet in a few Earth days, while the surface bakes beneath permanent cloud. Mars turns in a time close to Earth's, but keeps a thin sky. Storms there can grow large enough to wrap the globe, yet the planet cools quickly once dust lifts and light thins. These examples do not break the rule. They show how rotation joins with air heat and gravity to choose from many possible climates. Models that vary day length confirm the same sensitivity. Slow the spin, and day and night grow long enough to push atmospheres toward extremes, yet clouds can gather over the bright side and reflect light, saving the surface beneath. Speed the spin, and the deflection multiplies jets, slicing storms into smaller, faster pieces and tightening ocean gyres. There is no single perfect rate. There is a span where water remains liquid in many places and where winds and currents can distribute heat across basins and continents. Earth sits within that span, and the biosphere builds its timing on the planetary metronome. Habit also extends beyond the atmosphere. Rotation stirs the deep through tides that lean water toward and away from the moon and the sun. Friction with basins and coasts turns that leaning into standing waves and moving bores, filling estuaries with oxygen and food and clearing the shallows for new growth. Beaches, deltas, and marshes mature within this alternation. Eggs, spores, and larvae release on phases of the tide so that currents carry them where survival is best. The spin does not create the tide alone, but it turns the pages of the tidal book at a steady rate so that life can read it. Even stones keep the time. Trees record wind in the tilt of rings. Stalagmites layer mineral bands that brighten and dim with wet and dry seasons. Cores pulled from ice pack faint dust and ash into annual lines. In each archive, the day's rotation is the invisible writer moving air and water in ways that decide how much warmth and moisture arrive. Clocks in laboratories are delicate. These clocks are continents wide and deep in time, and all of them depend on the turning. The engine contains a paradox as calm as it is strict. The rotation that steadies climate also slowly changes. Tidal friction with the oceans and the pull of the moon lengthen the day by tiny fractions that accumulate across ages. Life answers by updating its timing mechanisms, not by holding a fixed schedule. A forest that grows under slightly longer days does not betray the shift in a single leaf. Yet the slow adjustment is there in pollen records, in migrating ranges, in the patient motion of shorelines. The path now bends from air and water to metal and fire. Deep beneath continents and oceans, molten iron turns and slides in patterns set by heat and by the planet's rotation. Those motions generate a field that reaches into space, diverts charged particles, and helps keep the upper air from eroding away. Rotation, therefore, does more than pace weather and biology. It forges the shield that lets both persist. Having seen how a day shapes climate and life, the inquiry turns inward to the dynamo that a spinning world sustains, and to the auroras that write that hidden motion into the night. Beneath continents and oceans, molten metal flows like weather, and a turning world forges a shield out of motion. At the center lies a small solid heart of iron and nickel wrapped in a deep ocean of liquid metal. Heat left from formation and renewed by slow decay rises through that ocean. Rotation persuades the rising and sinking into columns that lean and twist, organizing turbulence into spirals. Conductive fluid sliding through its own magnetic field makes electric currents. Those currents in turn strengthen the field. This feedback is the dynamo, a quiet machine requiring only heat conductor and a steady spin. The outcome is a dipole field loops that leave near one polar region and re-enter near the other, though the true geometry wavers and knots with time. The field inflates into space to meet a constant wind from the star. On the day side, the wind compresses the shield until its pressure balances the planet's own magnetic push. On the night side, the wind pulls field lines into a long tail that stretches for millions of miles, a drawn bow waiting for a spark. When magnetic lines of different origins press together, they can break and rejoin in new pairs. This reconnection turns stored magnetic energy into motion and heat, flinging charged particles along pathways toward the upper air, where those particles strike atoms glow. Curtains rise above polar circles, green and red from oxygen, deep violet and blue from nitrogen, silent weather written in light. Satellites watch the process in detail. A mission with 4 craft flies in a precise formation through the boundary regions to catch reconnection in the act, measuring electric fields, particle speeds, and the thin currents that lace the magnetosphere. Other observatories trace the belts of trapped particles that loop above the planet rings that swell and thin with storms from the star. When the star bellows, the belts can intensify, electronics complain, and power grids feel the stress. Space weather is not a figure of speech, but a system of storms born in plasma and guided by rotation's invisible architecture. Rotation matters because it steadies the flows in the deep. A world that turns organizes convection into helical paths that favor a large-scale field. The exact pace matters. A very slow spin gives the columns less guidance and can allow the field to break into small knots that cancel on large scales. A very fast spin can strengthen the dipole and sweep away complexities. The present world occupies a middle ground where the field holds a strong global character, yet wanders restlessly across centuries. Navigators update charts not only for coastlines but also for the moving curve where compasses point straight down. Rocks keep a diary of these changes. When lava cools or fine sediments set, magnetic grains align with the prevailing field and then freeze in place. Later, when those layers are found, the direction of their tiny compasses tells which way magnetic north lay at the time, and the strength of the imprint hints at how bold the field was. Seafloor maps reveal ribbons where the orientation flips from one stripe to the next, an alternating pattern written as new crust forms and moves away from mid-ocean ridges. The record shows that the field reverses many times, sometimes after long quiet intervals, sometimes in flurries of brief excursions. The switch does not happen in a night. It meanders and multiplies poles before settling, and life has passed through such episodes repeatedly. The surface feels these redistributions mostly through technology and sky glow. During a reversal, the shield weakens unevenly, not vanishing but developing windows where radiation climbs. Auroras migrate toward lower latitudes. Creatures that sense magnetic direction, migrating birds, sea turtles, perhaps tiny compass molecules in eyes, must rely more on star maps and odors and coasts. Satellites that skim the softened shield may need extra caution, yet the magnetosphere persists because the dynamo persists, and the dynamo persists because rotation and heat persist. Other worlds make the same argument by contrast. Mars carries remnant magnetism locked in ancient crust but lacks a global field today. Its small size cooled the core, the engine stalled, and the wind from the star has nibbled at its air for ages. A spacecraft that tastes the upper atmosphere there has watched ions stream away down the tail, an ongoing erosion written in light and charged particles. Venus rotates very slowly and in the opposite sense to its orbit, and though its interior may still move, the planet largely meets the stellar wind with an induced shield formed by currents in its dense ionosphere. Mercury, small and close to the star, keeps a weak but living dynamo that probes mapped in detail, a surprise that forced models to allow a partially molten layer and a delicate balance between cooling and stirring. Among giants, the lesson becomes emphatic. Jupiter spins in less than half a day and stirs deep layers where hydrogen becomes metallic. The result is a field so strong that it dominates a region larger than the star itself, a magnetosphere stuffed with particles stripped from a volcanic moon and accelerated to punishing energies. A polar orbiter has flown perilously close and found that the field is lopsided and patchy in places, as if emerging from a complex quilt of flows beneath the cloud tops. Saturn holds a dignified field aligned unusually well with its spin, a puzzle for dynamo theory that invites refinements to how symmetry can persist inside a turning conductor. Back at Earth, constellations of satellites map the field's quiet variability. A trio flying in polar orbits senses both the core's contribution and the drape of crustal magnetism from old rocks. From year to year, weak patches shift notably, a broad anomaly over the South Atlantic where the shield thins. Airliners root around storms aloft. Operators turn off sensitive instruments when passes through the belts become hot. Beneath these practical choices lies a simple persistence the field holds because the core turns and flows, and the core turns and flows because the planet rotates and cools. Animals answer the field with extraordinary subtlety. Iron-rich crystals in tissues point like tiny compass needles, and light-sensitive molecules form transient pairs whose chemistry changes with orientation in a field. From these small effects, turtles find rivers, birds cross oceans at night, and salmon read estuaries like maps. The signal they trust is not constant. It drifts as the poles wander, and yet the guidance endures because navigation is redundant and memory is broad. The planet's shield is more than armor. It is a landmark written in forces. All of this belongs to rotation's quiet work. A day measured on the surface becomes a gyre in molten iron, a voltage in space, an aurora on the night side, and a whispered direction in a migrating mind. The same turn that steadies weather also bends charged particles, paces the dynamo, and writes a moving chart across stone and sky. Having followed rotation inward to the field that guards the air, the path now turns outward and upward into places where turning does something stranger still. There near dense remnants and at the edges of horizons spin does not merely guide particles. It twists the very fabric through which light travels, and clocks change their pace in the whirl. Time does not sit idle beside a turning mass. It leans, it drifts, it follows a slow spiral, as if the fabric that carries seconds could be stirred by motion. general relativity provides the grammar for this behavior. Mass and energy shape geometry, and geometry tells matter and light how to move. When an object also rotates, the shaping acquires a twist. Nearby space and time are not merely curved downward like a valley, but drawn into a gentle swirl around the axis. An observer brought close finds that directions that once felt independent are now coupled as if invisible eddies tug on every path. This effect is subtle for a small, slowly turning world and profound for a dense, rapidly spinning remnant. The planet beneath ordinary footsteps offers a first quiet demonstration. Engineers place gyroscopes in orbit, their rotors polished and balanced until they become nearly perfect keepers of direction. Left alone in empty space, a gyroscope should point steadily, but the rotating Earth tugs at the surrounding space-time and persuades the axis to precess by a tiny amount. Laser-ranging to passive satellites and missions that fly instruments in careful formation have measured that drift. The angles are small enough to be counted in fractions of a degree over a year, yet they follow the predictions of a theory that was first written in the early 20th century and has since been tested wherever patience and precision allow. On the ground ring, lasers confined to quiet basements trap light in square or triangular paths. Two beams chase one another in opposite directions. When the apparatus rotates, the beam traveling with the turn sees a slightly longer road than its partner and their interference shifts. This Sagnac effect belongs to rotation itself. In combination with gravity, it becomes part of a larger truth motion mass, and spin together decide how clocks separate and rejoin across space. Navigation systems work only because their designers correct for these differences, continuously comparing signals from clocks high above a turning Earth with clocks resting on its surface and adjusting for both speed and gravity. Move outward and the twist gathers strength. A white dwarf star compacts a solar mass into a body the size of a planet. A neutron star compacts even more into a sphere no wider than a city. Many of these remnants rotate hundreds of times each second. Their gravity bends light so strongly that the far side is partly visible from the near side. Their rotation drags nearby space-time into a whirl. Hot spots on their surfaces rise and set under a warped sky, and instruments that measure X-ray pulses reconstruct the shape and spin by how those pulses stretch and skew. Time itself runs measurably slower at such surfaces than in the quiet between stars, and the rotation adds a directional pull to that slowing, a frame dragging that nudges trajectories and phases. Matter spiraling toward a compact object carries its own memory of orbits, a sequence of preferred lanes that ends abruptly at an inner edge where stable paths cease. For a non-rotating mass, that edge lies farther out. For a rapidly spinning mass, it moves inward. The difference changes the color and brightness of the glow as friction heats the inward plunge. It also imprints small rhythms in the light quasi-periodic oscillations linked to precession set by the twisted geometry. Observatories in orbit have watched these flickers repeat with surprising regularity, as if listening to a drum played by gravity and spin in duet. At the scale of a supermassive black hole, the duet becomes an orchestra. Gas near the center orbits at a significant fraction of light speed. Magnetic fields thread the flow and launch jets that climb out along the rotation axis, sometimes for distances larger than an entire galaxy. The launching geometry is not arbitrary. The field lines wind because the disk turns, and the disk turns in a space-time that itself is being drawn around by the central spin. Where the field meets that dragged space-time energy can be tapped and collimated, and the beams remain narrow across enormous distances. Closer still to the horizon, the swirl becomes inescapable. Even an observer who tries to hover must turn with the flow because the local definition of standing still has changed. This enforced co-rotation does not yet mean a one-way fall, but it does mean that inertia has been rewritten by rotation. In the next chapter, that region will receive a name and a boundary, but for the moment it stands as a threshold where the partnership between spin and gravity stops being delicate and becomes decisive. The influence of rotation on time is not only a spectacle near extremes, it is present in quieter places that instruments can visit. Atomic clocks flown in aircraft and placed on mountains have recorded that motion and altitude both change the tick. The differences are tiny, yet they accumulate and can be read like the faint print of an embossing plate. A clock at the equator moving fastest with the surface experiences a slightly different blend of speed and gravity than a clock high on a calm plateau, and careful comparisons recover that distinction. These experiments are not ornaments to theory. They are necessities for systems that knit together a planet with timing accurate to billionths of a second. Even the turning of a satellite's orbital plane around a spinning world is touched by the effect. Paths that would otherwise repeat exactly shift by small amounts with each circuit. Mission planners include that precession when designing lifetime's ground contact patterns and the geometry of future encounters. The sky writes bookkeeping into every orbit, and the entries include a line for the twist of space-time itself. Astronomers also listen to rotations that cannot be directly seen. Networks of radio telescopes time the pulses from millisecond neutron stars and compare arrival times over years. Minute departures from perfect regularity can signal ripples in space-time passing between source and listener, often released by supermassive black holes and slow in spiral. The clocks are stellar, the detectors are planetary, and the messenger carries information about mass, distance, and spin. In this way, even very slow, very large rotations announce themselves through their influence on the flow of time across vast baselines. Piece by piece, the picture settles. Rotation does not only set days and winds, it sculpts the geometry that hosts light and motion. Near Earth, the sculpture is delicate and must be coaxed into view by gyroscopes and lasers. Near remnants, it becomes architecture, commanding the paths of matter, the color of radiation, and the tempo of clocks. The same law speaks at all scales where mass turns space-time follows. The next step is to cross the threshold hinted at here to enter the region around a spinning black hole where even a determined engine cannot hold its place against the swirl. There, standing still becomes impossible by definition, and motion is not chosen but required. That border and the strange exchanges of energy it permits wait just ahead. A border around a spinning darkness behaves like weather made of geometry, a place where standing still is not allowed and every path must join the swirl. The region carries a name that suits its effect. Outside the event horizon, but inside a larger pear-shaped surface, space-time is dragged so strongly that no object can remain motionless with respect to distant stars. The limit of possible stillness is called the static boundary, and the zone between that boundary and the horizon is the ergosphere. Within it, the local definition of rest has tilted. Light cones, lean inertial frames rotate, and even a patient engine pointed against the flow can only choose how swiftly to co-rotate, not whether to do so. The cause is not a wind through matter, but a twist in the fabric that hosts matter and light. This twist allows a strange accounting of energy. Inside, the ergosphere paths exist on which the conserved energy measured from far away can be negative. If a single body enters and divides into two fragments, one fragment can fall inward on such a path, while the other escapes with more energy than the original carried. The gain is paid by the black hole's spin, which is reduced by an infinitesimal amount. This is the Penrose idea in its cleanest form. Rotation can be mined when geometry itself offers a ledger with negative entries. In the sky, the clean splitting of stones is unlikely, but fields can play a similar game. Magnetic lines threading an accretion disk and dipping into the ergosphere can extract rotational energy continuously. Where plasma ties field lines to the turning spacetime currents form, and a pointing flux climbs away along the axis. The process launches narrow jets that hold together across distances larger than their host galaxies. The details carry names in textbooks, but the picture is simple: spin wins field. Field channels energy. Energy escapes as a beam. Observations of active galactic nuclei show jets that remain collimated for hundreds of thousands of light years, their power waxing and waning as the inner disk reorganizes. The Event Horizon Telescope has measured polarized light around the central darkness in Messier 87, revealing ordered magnetic structure consistent with such extraction. Rotation also shifts the edge of stability for orbits. Where no spin is present, the innermost safe circular path sits farther out, and the efficiency of accretion, the fraction of falling mass, turned into radiant energy, hovers near 6%. For material that spirals prograde around a fast spinner, the safe edge moves inward, and the efficiency climbs towards several tens of percent. The glow therefore hardens and brightens as spin increases, and the rhythm of flickers in the light bears the imprint of precession driven by the dragging of frames. X-ray spectra from disks around stellar mass black holes carry iron lines stretched into long red tails and skewed blue horns, a signature of extreme speeds, strong gravity, and the asymmetric lensing produced by rotation. Closer still, the ergosphere sets the stage for superradiance, where waves can emerge with more energy than they brought. If a coherent wave enters the region with the right pattern, it can be amplified by the turning geometry and return stronger. In thought, a mirror placed around such a system could trap and grow the wave, a fantastical engine sometimes called a black hole bomb. In nature, there is no mirror yet. The same principle hints that certain fields or ultralight particles, if they exist, could tap spin and leave gaps in the astrophysical distribution of rotation. The idea remains a careful speculation, but it shows how deeply motion can couple to the simplest disturbances. On the largest accessible scales, the consequences of the swirl are written into delays and echoes. Flares near the inner disk light up the gas. Some photons scatter off the disk and return later by bent routes. The time between flash and echo depends on height, spin, and the position of the safe inner edge. Observatories have begun to use this reverberation as a ruler, mapping the geometry by listening to light arrive in 2 acts. In a different band radio, interferometers trace bright knots that seem to orbit just outside the darkness. Their apparent speeds and periods, when translated through the lensing caused by spin, offer independent hints of the rotation rate of the central mass. A point bears repeating: the ergosphere is not the horizon. Escape remains possible there, but only by joining the motion that space-time demands. The distinction matters for energy extraction and for the shapes of jets. It also matters for the paths of stars and clouds that come too close. A star brushed by tides can shed gas that wraps into a disk. The early spirals carry clear evidence of frame dragging as their planes precess, and their bright clumps shift phase in ways a non-spinning geometry cannot mimic. The influence reaches beyond spectacle into plain necessity. The alignment of jets with the rotation axis steadies as spin grows, guiding feedback that can starve or feed the host galaxy's central regions. The power released by efficient accretion seeds magnetic turbulence that in turn governs how material can lose angular momentum and drift inward. Even the distribution of elements in the wind blown from the inner disk depends on where the safe edge lies, and thus on how rapidly the center turns. Rotation chooses not only the brightness of the deepest engine, but also the chemical weather felt far away. At human scales, the same mathematics remains present in gentler form. Precision compels navigators to account for frame dragging in the precession of orbits and in the clocks that knit positioning networks together. Ring lasers in quiet rooms sense the planet's rotation through phase, the miniature sibling of the Grand Sagnac shift that would be felt by light circling a black hole. Atomic clocks flown and returned teach the same lesson over and over. Time is part of the medium that motion can stir. In this landscape, the idea of stillness has no footing. Near a spinning horizon, the only choices are curves that carry one along or curves that carry one in. Yet the very lack of stillness enables structure jets that thread clusters, disks that shine with high-efficiency echoes that serve as rulers, and polarization that betrays wound fields. The ergosphere is both prohibition and permission, a ban on rest and a grant of pathways by which energy can leave a place that otherwise hoards it. From here the path widens away from the extremes. The next turn in the story asks how such decisive effects arise from tiny beginnings. A universe that seems smooth at first glance becomes laced with preferences as it cools, small tilts, small imbalances, small broken symmetries that seed every later pattern. Rotation makes those seeds loud near horizons. Elsewhere they whisper, yet the whisper proves enough. The inquiry now leaves the edge of the hole to follow the far older rule that a slight bias can grow into a world. A tiny tilt breaks the mirror, and from that quiet fracture the universe wakes to structure, motion, and time. Perfect balance would freeze everything. If every direction matched every other, if every charge had an equal partner, if every fluctuation were cancelled by a twin, then gravity would have no foothold, chemistry, no preference and motion, no reason to begin. The early cosmos does not choose that path. It cools out of a hotter state and lets small asymmetries take root. The result is not disorder but possibility. With the first imbalance, forces separate, fields settle, and tiny gradients invite movement. The oldest light in the sky holds the first evidence. The cosmic microwave background arrives almost uniform, yet not entirely. Across that soft sea temperature varies by about 1 part in 100,000. These specks of difference are not blemishes, they are instructions. Regions with the slightest extra density pull a little more strongly, and over long time those pulls become filaments and knots, clusters and voids. A universe that is nearly even becomes richly uneven because gravity rewards small advantages without ever spending them down. Symmetry does not only give way in density, it also relaxes within the forces themselves. In the hottest moments, what later become distinct interactions share a single stage. As expansion proceeds and temperature falls, that unity cracks. The field that gives particles their masses acquires a non-zero value, everywhere a choice among many equivalent possibilities. In making that choice, the universe breaks asymmetry and becomes specific. Masses appear. Pathways for decay and interaction change. The world steps away from a perfect mirror toward a story that can continue. The existence of matter at all requires a deeper slant. When a hot plasma can produce pairs of particles and antiparticles with ease, the natural expectation is that later, as the cosmos cools, those pairs annihilate in equal measure and leave only light. Instead, a tiny excess of matter survives. For roughly every billion pairs, one extra particle of matter remains unmatched. That 1 in a billion is everything that later forms stars and worlds. Such an outcome demands that the rules treat matter and antimatter just a little differently under particular conditions, and that the early universe provided those conditions. Laboratories have caught glimpses of this preference. Certain decays show that the combination of reversing charge and reversing spatial parity does not always restore equivalence. The phrase for this is charge parity violation. It is measured in delicate experiments with unstable particles that live for fractions of a second and yet speak clearly about a universal bias. These measurements are not the whole story of how the excess of matter formed, but they are proof that nature allows the needed tilt. Patterns in the oldest light also carry directional hints. Beyond temperature, the ancient glow is polarized because the last scattering of photons from free electrons preferred some directions within that polarization curl, like motifs can appear. Some are made by intervening structure lensing the light. Others, if present, could be fossils from the first stretches and squeezes in space-time itself. The search for those curls has driven instruments to high plateaus and dry valleys, and the conversation remains careful because the signal, if it exists, is both faint and vulnerable to foreground dust. Still, the method is precise. Read the geometry of the dawn in the orientation of surviving light. Asymmetry also grows from tidal interactions that harvest the imbalances already present. When a patch of matter collapses under gravity, its neighbors are not evenly placed. Their lopsided pull applies a torque. The forming structure acquires spin, not from an imposed command, but from a bookkeeping of uneven surroundings. Numerical experiments that start with tiny random variations and nothing else produce a cosmic web dotted with disks and halos whose rotations arise this way. The lesson is steady: give gravity time and asymmetry, and rotation appears without being asked twice. On galactic scales, additional patterns tempt interpretation. Samples of distant spirals can show slight preferences in the handedness of their winding when collected over immense volumes. The effect is subtle, and selection, biases, and calibrations must be tested, yet the very possibility points back to origin. If the beginning permitted even the faintest preferred orientation, later growth could amplify it into statistical quirks that surveys might someday confirm with certainty. The current balance of evidence still favors a cosmos that is nearly isotropic, with any global rotation pressed below strict limits, but the door for delicate relics remains open. Closer to home, the consequences of broken symmetry reach into chemistry. The weak interaction that indulges charge parity violation also favors one-handedness in the way certain particles align their spins. In a universe where left and right are not always equivalent, molecules can inherit preferences. Ultraviolet light that is polarized by dust and magnetic fields in star-forming regions can destroy one mirror version of a precursor more efficiently than the other, leaving a small excess behind. Meteorites have delivered such imbalances to hand a quiet note that cosmic processes can pre-select ingredients long before biology begins. Even where the equations remain balanced, history can break symmetry by choice of initial conditions. Imagine a pencil standing on its tip. The laws allow it to fall in any direction. The actual fall, nudged by the smallest tremor, becomes the seed of a larger structure lying specifically to one side. The early universe, emerging from hot simplicity into cooler complexity, faces many such poised decisions. Each time it leans later, structures remember. Fields freeze with a particular orientation. Domain walls decay. Bubbles of one phase grow at the expense of another. None of these episodes needs a grand intention. A small push and sufficient time suffice. The accumulated effect is a world where motion has direction, matter outnumbers antimatter, and structures prefer certain alignments when conditions encourage them. The striking part is that the required tilts are tiny, 1 part in 100,000 births a skeleton for galaxies, 1 in 1 billion selects matter over light. A mild preference in spin at subatomic scales echoes upward into the chemistry of complex molecules. Asymmetry is not an interruption of nature's grace. It is the reason nature can build. Speculation remains as it should. Perhaps fields beyond those already known carried time-dependent angles that biased reactions in the first seconds. Perhaps ultralight particles formed clouds around young black holes and stole their spin, leaving notches in the distribution of rotation that future surveys will see. Perhaps alignments in the oldest light will harden into a pattern that demands a revision of the simplest early history. Pending answers, the conservative picture holds small asymmetries grown by gravity and guided by conservation are sufficient to explain the broad strokes of what is seen. From broken symmetry, the path narrows toward life. If physics prefers a direction in minute ways, does chemistry obey that preference when it chooses between mirror molecules? Do tiny tilts in starlight and fields in dusty nurseries leave fingerprints in the building blocks that rain down on young worlds? The next inquiry turns to that interface between cosmos and cell, where a spiral of information inside every organism may carry the memory of ancient one-sided choices written into the universe at the very beginning. Inside every cell a spiral chooses a side, and that quiet choice reaches back to starlight, dust, and fields older than oceans. Life on this world is one-handed. The helical molecule that stores genetic instruction typically winds to the right under ordinary conditions, while the small building blocks that knit into proteins are almost exclusively left-handed. Mirror forms exist in principle, yet biochemistry prefers a single orientation with a loyalty so complete that even tiny intruders of the opposite hand can disrupt function. This uniformity, called homochirality, is not demanded by the bare rules of chemistry. It is a history written into chemistry, a decision made somewhere between space and the first warm waters, where complex reactions gathered speed. A mirror choice matters because molecules that are mirror twins do not behave the same in a living context. One form can fit a receptor while the other does not. One turns the plane of polarized light this way while the other turns it that way. Enzymes, the catalysts that guide reactions gently along, are themselves chiral and will welcome one hand while ignoring or hindering the other. Once a preference takes hold, feedback strengthens it, since the tools that build with one hand are also shaped by that same hand. The puzzle is how the first tilt arose before life could reinforce it. Space supplies plausible nudges. In star-forming regions, light can emerge with a twist. Dust aligned by magnetic fields and shaped by rotation can polarize ultraviolet radiation so that it carries angular momentum in a preferred sense. When such light passes through clouds rich in simple organics, it can break apart one mirror form slightly more often than the other. Over long spans, even a small bias accumulates. Laboratory experiments have mimicked this with beams of circularly polarized light and mixtures of prebiotic molecules, finding that gentle excesses can be seeded and then amplified by further reactions. Stones from space arrive carrying records. Meteorites that fell in the 20th century preserved amino acids not known from earthly contamination, and some samples showed a small surplus of left-handed forms. The surplus was not enormous, yet it was clear and consistent across species of molecules. The message was restrained but unmistakable. The materials that rained onto young worlds were not perfectly balanced. Comets add to the narrative. A spacecraft that rendezvoused with a short-period comet sampled vapors and dust and found a suite of organic compounds complex enough to play roles in prebiotic chemistry. Another mission returned grains from a primitive body rich in carbon and volatile molecules. Together, these lines of evidence suggest that the raw inventory delivered to early oceans already leaned, however slightly, toward one hand. Once a seed bias exists, several mechanisms can magnify it. Crystals of certain amino acids can separate mirror twins into distinct faces, and one face can catalyze reactions that favor its own orientation. Solutions that evaporate and rehydrate can select for one form by minute differences in solubility. In icy pores within rocks, repeated freezing and thawing can concentrate one hand over the other. Tidal pools that cycle through wet and dry phases under a short day and a strong moon can offer the same selective furnace. In each case, the planet's rotation and its rhythms of light and tide provide the metronome for gentle repetition, and repetition allows small preferences to become working rules. The handedness of sugars adds another layer. The backbones of nucleic acids employ sugars that are mirror opposite to the amino acids that build proteins. That complementary arrangement permits clean recognition between strands and enzymes. Right-handed helices of genetic material pair naturally with left-handed protein shapes that read, copy, and repair them. The system behaves like locks and keys carved by the same artisan. Change the handedness of one set and the correspondence falters. That interlock is not inevitable from first principles. It is a stable architecture that grew from early selections and then persisted because it worked. The weak nuclear force, which at fundamental scales distinguishes left from right, offers a deeper echo. In particle physics, certain decays prefer one orientation, breaking a mirror symmetry that once seemed sacred. The effect in chemistry is extraordinarily small, far below what ordinary reactions would notice. But the existence of any physical distinction between left and right assures that handedness is not an illusion of language. The universe itself contains a bias written into its interactions. Between that bias, twisted starlight magnetic fields, and the long patience of cycles on a rotating world, there is room for a path from slight asymmetry to living order. Biology today still listens to these cues. Migratory animals carry nanoscale compasses built from iron-bearing crystals and light-sensitive molecules whose reactions change with magnetic orientation. Their maps are redundant and robust, yet part of their guidance comes from a field ultimately forged by a rotating core. Plants wind tendrils and open leaves by internal clocks phased to the 24-hour day. Coral reefs spawn on nights set by the tide and the moon. The great spiral within the nucleus does not merely store sequences. It keeps time with the planets turning and the sky's gentle cycles, a choreography that places each chemical act within the right hour. If this chain of influence seems stretched across too many scales, the archives bring it back to hand. In thin slices of meteorite, tiny inclusions record magnetic fields that threaded the disk where planets were born. Those fields were shaped by rotation and linked to jets that carried angular momentum away. In cold interstellar ices, laboratory spectra show chiral precursors that respond differently to left-handed and right-handed light. In sediments on Earth, layered minerals and trapped organic compounds remember tidal and seasonal rhythms that served as reactors and calendars for early chemistry. Each archive speaks softly, but together they read like chapters of the same book. The logic does not insist that life everywhere must share the same orientation. It allows that different nurseries, fields, and histories could select the opposite hand. Yet it predicts that any living chemistry will make a choice and then hold to it because coherent machines must standardize their parts. Should a sample from another shore in the cosmic ocean someday reveal mirror-reversed biochemistry, it would not refute the pattern. It would complete it, showing that handedness is a rule that can be fulfilled in two ways. From the spiral within the cell, the story can widen again. The same universe that imprinted a molecular lean also set galaxies into rotation. Those galaxies, when measured carefully, spin too fast in their outskirts for their visible matter to bind them. An unseen framework must be present, adding gravity without light, a quiet scaffold upon which disks and bars can survive their whirl. The path thus turns from the interior of life to the architecture of the sky, where rotation again exposes a hidden partner that steadies motion others cannot explain. A hidden scaffold holds fast spinning disks together as if gravity had a second quieter hand that does not shine yet never lets go. The clue arrives where rotation refuses to taper. In a simple picture, stars close to a galactic center should circle quickly, while outer stars should slow just as distant planets move more gently around a star. Observations do not oblige. Long slits across spiral galaxies yield curves that rise and then flatten, remaining nearly level far beyond the bright arms. The outer stars move too fast for the visible mass to bind them. Either gravity changes its rules at low accelerations, or there is more matter than starlight reveals. The latter path gathers evidence from many directions and becomes the working frame halos of unseen mass embrace each galaxy, extending far past the luminous disk, adding the gravity needed to hold the whirl. The idea first takes a public shape in the early 20th century, when a cluster of galaxies appears too lively to stay bound by the light it shows. Later in the late 1970s, careful measurements of spiral disks chart speed versus distance with patience and precision. The lines refuse to fall. In that refusal lies the first modern map of what will be called dark matter. The name is modest. It does not pretend to know composition. It says only what the phenomenon is not. It is not bright, not absorbing, not scattering enough to betray itself by glow or shadow. It declares itself through gravity alone. Gravity, however, is generous with proofs. Where a massive cluster lies between distant galaxies, and the observer light from the background stretches into arcs and rings. The geometry and strength of this lensing demand mass far beyond what starlight and hot gas can muster. In a famous colliding pair of clusters, the glowing gas lags behind after impact, while the bulk of the gravitation traced by lensing leads ahead. The separation argues for a component that passes through the collision with little friction, interacting weakly with itself and with ordinary matter. Rotation predicted the problem. Lensing sketches the answer's outline. Simulations that begin with the early universe's faint density, ripples, and include a cold, slow-moving, non-luminous component grow a web whose strands and knots resemble the observed distribution of galaxies. Dark halos form first, then gather gas that cools, spins, and settles into disks. Bars, rings, and spirals arise within those disks, but the overall stability against centrifugal flight belongs to the broad, roughly spherical halo. The halo's reach explains why dwarf galaxies near large hosts can retain fast outer stars despite their meager light, and why tidal streams from torn satellites trace orbits that imply deep extended wells of gravity. Rotation continues to serve as a meter, In the outskirts of many spirals, hydrogen gas emits a faint radio whisper at a wavelength chosen by atomic structure. Radio arrays listen to that line across vast diameters and confirm that flat rotation curves persist beyond the last visible stars. The gas moves as if riding the rim of a wheel far larger than the bright disk. In low surface brightness galaxies where starlight is sparse, the mismatch becomes even more striking, and the need for an unseen mass or for a change in gravity becomes hard to avoid. Alternatives to new matter exist and receive careful trials. Some proposals adjust the way gravity behaves at very low accelerations tuned to recover the flat curves without halos. Such schemes can match individual rotation profiles but struggle to accommodate the whole constellation of lensing cluster dynamics, cosmic background patterns, and the growth of large-scale structure. The conservative picture remains that an unseen mass component dominates the accounting, while the exact particle nature stays open and under search. Experiments dig downward for a direct encounter. Deep underground detectors wait for a rare tap on a nucleus by a passing dark particle. So far the silence holds and limits sharpen. Astronomers look upward for subtle gamma-ray glows or X-ray lines that might arise when dark partners annihilate or decay. Hints appear and fade as instruments improve and the galaxy's conventional emissions are modeled more accurately. The search remains active on both fronts because the gravitational case is strong and because the particle answer, when found, would link the cosmic scaffold to a laboratory fact. Meanwhile, new surveys map the scaffold by its influence on light paths and galaxy shapes. Weak lensing slightly stretches millions of distant galaxies in correlated ways. Statistical care turns those faint shears into a three-dimensional chart of mass across billions of light years. Space missions chart this pattern over wide fields, while future observatories promise deeper reach and sharper tests. If dark matter behaves exactly as a cold, slow component, the maps should follow one script. If small departures appear perhaps from a particle that is not entirely cold or that sometimes interacts, the pattern of small-scale structure will carry those edits. Rotation, once the spark of the mystery, becomes one of several cross-checks that together constrain the invisible. The halo also moderates the inner life of a galaxy. When bars form in disks, they can transfer angular momentum to the surrounding dark envelopes, slowing as they strengthen. Gas that drifts inward along bar lanes fuels central starbursts or wakes a compact engine, and the balance of those inflows depends on how the halo's gravity shapes the disk. Satellite galaxies orbit within the halo's pull and slowly sink as they lose energy to tides and to the wake they raise in the dark sea, a process that rearranges both the satellites and the host building thick disks and faint stellar halos over time. Dwarf galaxies push the framework to its edge. Some show central regions where the mass profile is shallower than the simplest simulations predict. Feedback from supernovae can reshuffle central matter and soften cusps into cores, but the range of outcomes keeps theory honest and lively. Satellites around large spirals sometimes appear in flattened planes, a geometry that prompts debate about chance alignments, selection effects, and the legacy of ancient group infall. Each anomaly is a test. Many resolve with added data or with more complete modeling that includes gas star formation and feedback. A few remain as invitations to look again. Through all this, the guiding picture stays economical. A halo of unseen mass surrounds each luminous disk, binding fast outer rotations and governing how material flows over cosmic time. Clusters carry this invisibility in bulk. Filaments stretch it between clusters. Lensing rotation and large-scale maps point to the same scaffold. The composition remains unknown, but the role is unmistakable, the quiet hand that steadies every whirl. From this scaffold the story turns to exchange. Spins are not static possessions. Collisions, tides, bars, and jets shuffle angular momentum between stars, gas halos, and the dark sea. Over billions of years, disks thicken, bulges grow, and orbits change their shapes. The next inquiry follows these trades, asking how a cosmos built on rotation slowly rearranges that rotation, and how dances between partners end in systems more settled, rounder, and in time quieter. Rotation is not a hoard, it is a currency that systems trade until shapes, orbits, and rhythms change their character and become quieter. Begin with a barred spiral whose bright lanes cross its center. The bar is a wave of stars and gas that rotates as a single figure. As it turns, the pattern exerts gentle torques on the disk and on the unseen halo around it. The wave hands angular momentum outward to distant orbits and to the dark envelope, and receives angular momentum from inner regions in return. Gas, losing some of its share, slips along the bar toward the center, where it thickens, forms new stars in a brief blaze, or feeds the compact engine that waits there. The bar grows more massive as it slows a trade written into the changing length of its arms and the hush that follows a burst of activity. Spiral waves play a similar game. A crest moves through the disk more like a traffic pattern than a solid feature. Stars drift in and out of the crest, but the wave carries torque-shifting angular momentum from one ring to the next. In this bargaining, some orbits circularize, while others grow more elongated. A star that began life on a tidy circle can migrate radially without becoming violently scattered, ending its days under a sky of different constellations while remaining part of a thin ordered disk. The disk thickens gradually as many such small trades accumulate over billions of years. Dynamical friction provides the slow break in crowded places. A globular cluster or a small satellite galaxy moves through a sea of stars and dark matter, raising a wake behind it. That wake pulls back, stealing orbital energy and angular momentum from the traveler. Over long times, the satellite sinks inward, where tides tear it into streams that wrap around the host. The streams remember the original path as arcs and shells embroidered across the halo. Each thread marks momentum surrendered by a smaller body and absorbed by the larger system's collective motion. When two large galaxies meet, the exchange becomes sudden and decisive. Their stars rarely collide, but their orbits feel every passing mass. The encounter mixes the old patterns, unbinding some stars into long tails and folding others into a swollen bulge. Gas shock, heated and torqued, can lose angular momentum rapidly and fall toward the center, where it lights a brief quasar or a fierce starburst. The overall figure that emerges tends to be rounder and more slowly rotating than either of the ancestors, a record of how a pair of disks used their spin to pay for a new equilibrium. Within the same story, black holes at the two centers spiral toward one another through dynamical friction against surrounding stars and gas. As their orbit tightens, three-body encounters fling stars outward with stolen angular momentum, carving a shallower core into the remnant and further draining the pair's orbit. In the last stages, the black holes shed the remainder as waves in space-time. When they finally fuse, the remnant can recoil with a small kick set by any mismatch in the spins and masses, a final adjustment in the ledger before the new center settles. Tides perform their arithmetic more gently but no less firmly. A moon raises a bulge on its planet. The bulge lags behind the line joining their centers because the planet rotates. That lag torques the moon, adding orbital angular momentum, and pushing it outward while the same torque slows the planet's day. The ocean and the mantle dissipate energy as heat, yet angular momentum is conserved by slipping from spin to orbit. Over eons, a lengthening day and a widening lunar path testify to the trade. In compact planetary systems, similar negotiations can lock rotations into resonances or drive planets into mutual dances that either stabilize long-term or end in close encounters and expulsions. Rings around giant worlds reveal the physics in miniature. Small moons just outside a ring can add angular momentum to its outer edge and confine it. Resonances inside the ring launch spiral density waves that march inward or outward, redistributing the motion of countless icy particles. Shepherd moons trade momentum with narrow arcs, holding them together against spreading. The rings are thin, bright laboratories where torque dissipation and conservation rehearse the same principles that shape galaxies. Stars themselves change their spin through winds and magnetic tethering. Young suns rotate quickly until their magnetic fields bite into surrounding disks and fling angular momentum outward along open lines. Later, a steady wind carries away a stream of charged particles that drags on the field and slows the surface. The spin of a star, therefore, keeps time with age composition and magnetic vigor. In close binaries, tides can synchronize spins and orbits so that both faces become mutually familiar, while mass transfer through a shared envelope can spin one star up to remarkable speeds and leave the partner swollen and slow. Inside galaxies, feedback from stars and from central engines feeds back into the exchange. When supernovae and stellar winds stir the inner gas, they can puff up central dark matter and ease the steepness of its profile, changing how angular momentum is stored and transferred. When a compact engine launches a jet, the direction of that jet, aligned with the spin axis, can heat gas in the halo and slow its return to the disk-starving future star formation and altering the community of orbits that would otherwise have grown. Rotation given away at the center can rearrange the outskirts by changing how gas cools and flows. Even where collisions are rare, long resonances do their work. A small persistent pattern can trap orbits and swap angular momentum across great distances. Over time, populations of stars peel away from the thin disk and occupy thicker layers, while others settle into rings and lenses that mark past resonances like the faint outlines of waves on hardened sand. The current form of a galaxy is therefore a palimpsest, a layered record of many slow trades and a few large mergers, with rotation passed back and forth until structures round off and motions grow more random. The same destination appears at larger scales. Galaxy groups merge into clusters, and clusters relax towards smoother, rounder shapes through violent relaxation, an oddly named but statistical process in which many small gravitational tugs redistribute energy and angular momentum among countless orbits. Individual spins do not vanish. They are spread among many bodies, orientations, and radii until the system's figure stops changing quickly. Motion remains, memory remains, but the drama fades into equilibrium. In each case, the principle is spare and consistent. Angular momentum is conserved, but it is not conserved where it began. Bars pass it to halos. Satellites pay it into wakes. Disks exchange it through waves. Moons borrow it from days and repay it to orbits. Black holes surrender it to ripples that run for billions of light years. Over long spans, these trades settle systems into rounder, slower, thicker forms. Rotation does not end, it diffuses. Across the next horizon, the diffusion becomes a message that travels without a medium. When massive pairs conclude their long exchange, the last share of their angular momentum leaves as waves in space-time. Those waves stretch and squeeze distances in a rhythm that carries the imprint of mass spin and geometry. To follow the story of rotation to its quietest, most faithful messenger, the ear must change from light to gravity and learn to listen. A ripple passes without a medium, and yet whole constellations of mass answer, as if rotation could send its signature through the dark the way sound moves through air. When two heavy bodies circle one another, they do not keep their secret. With each turn, they disturb space-time itself, sending waves that stretch and squeeze distances by amounts too small for ordinary senses, yet large enough for instruments built with unwavering patience. The pattern of those waves preserves the entire conversation of the pair. Early, while the orbit is wide, the rhythm is slow and the amplitude small. As energy is shed, the bodies spiral inward. The pitch rises, the loudness grows, and the final moment peaks in a brief flare followed by a fading ring. In that single sweep from low to high, the imprint of angular momentum appears in bends and beats that decoding can read. On Earth, long tunnels hold laser light between mirrors that hang as if weightless. Each beam takes two paths at right angles, then reunites so that any change in distance along one arm compared with the other writes itself as a shift of light and dark. When a wave passes, one arm lengthens while the other shortens and the interference flickers. A series of such observatories in distant lands listens together so that the sky position can be triangulated and the polarization traced. With the first detections, the language of gravitational waves becomes not theory alone, but a channel of observation, and rotation speaks clearly. Spins tilt the orbits and make them precess. The plane of motion slowly wobbles, modulating the wave as if the source were a lantern sweeping a beam. In some pairs, the individual spins of the bodies line up with the overall angular momentum and speed the approach. In others, they lean against it and delay the plunge. The difference registers as a shift in how quickly the pitch rises and as small sidebands in the signal. From those details, analysts recover estimates of spin magnitudes and angles. A black hole that whirls quickly drives the innermost safe orbit closer to the horizon and changes the timing and color of the final ring, a ring whose tone depends only on mass and spin. Neutron stars add texture. They are heavy enough to curve space-time strongly, yet they hold matter in a state where pressure and quantum rules compete. When two such stars close in, tides deform them. The deformation alters the late spiral in a measurable way, softening the final ascent of pitch. That softening is a fingerprint of the stiffness of ultradense matter and the remnant's outcome, whether a short-lived hypermassive star or an immediate collapse into a black hole, changes the high notes of the ringdown and the glow of matter flung outward. In a few events, telescopes have followed the fading light of heavy elements forged in the aftermath, an electromagnetic echo guided by how angular momentum was partitioned when the cores met. Supermassive pairs whisper at far lower frequencies. Their orbits take years to turn, and their waves have periods measured in months. No ground instrument with kilometer arms can sense such slow undulations. Instead, the cosmos itself provides a metronome, millisecond pulsars, neutron stars that spin hundreds of times each second beam, radio pulses with remarkable steadiness. Arrays of these clocks scattered across the sky register tiny delays and advances when a wave washes through the space between them and Earth. By comparing many clocks over many years, astronomers recover a common correlated drift, a background likely made by countless giant binaries scattered through the universe. In that deep hum, the history of galactic centers and their long exchanges of angular momentum becomes a measurable field. A future observatory will open a middle octave in space. 3 spacecraft flying millions of kilometers apart will trade laser light across the near vacuum, forming a triangle that slowly rotates as it follows Earth around the Sun. This geometry will hear the slow songs of white dwarf pairs, within the galaxy the tumbling dances of black holes, 1,000,000 times the Sun's mass in distant nuclei, and the intricate orbits of small bodies, captured close to larger ones, in extreme mass ratio in spirals. Those small travelers trace thousands of tight loops while slowly sliding inward, and each loop samples a different part of the twisted geometry around a spinning black hole. The resulting waveform becomes a cartographer's kit, allowing the spin, the tilt, and even subtle departures from ideal symmetry to be mapped with care. Angular momentum does not only shape the sound, it is carried away by the sound. In the final beats of a merger, the waves themselves remove the last share of spin and orbital motion, leaving the remnant calmer. The direction of the lost momentum can be asymmetric, and the newborn black hole can recoil, sliding through its host with a measured kick. If the spins of the parents were misaligned, the kick can be strong enough to displace the remnant from the center, and the afterglow of gas can show a shifting line as the engine wanders and then sinks back. In other cases, the energy released in waves briefly outshines all starlight in the observable universe, a transformation of motion into radiation that uses no medium, only geometry. There are stranger notes to catch. The nonlinear memory of a burst leaves a permanent change in separation between freely falling points, a lasting offset written into space-time by the passage of the wave. Detectors on Earth glimpse this effect within their noise, while pulsar timing arrays aim at the slow accumulation of memory across many sources. A clean observation would be the quietest confirmation that motion can become memory in an exact, measurable way, not as metaphor, but as a step in the equations. Across instruments and bands, a catalog grows. Each entry lists masses, distances, spins, and sky positions. Patterns emerge. Some black holes favor high rotation, others reveal modest turns. Some binaries show precession, others are nearly aligned. With time, the distribution of spins becomes a population statement about how stars collapsed, how gas fed, and how pairs met and merged. The waves write a census of angular momentum through cosmic history, complementing what light already says about disks, jets, and tides. What began as a theorem now serves as a sense. The universe can be seen by hearing, and hearing restores motion to view, even when no light escapes. Rotation, once inferred from the shapes of galaxies and the timing of clocks, now arrives as direct rhythm. The last step is to reflect on what such rhythms mean beyond measurement. If waves leave a permanent trace, if fields hold a record, and if matter and light both carry the results of ancient turns, then motion is not only action, it is inscription. The path therefore curves toward the closing thought, how a universe that never stops moving writes its history into everything within it, and how awareness itself might be one way that history is read. Memory is motion held in place long enough to be read, and a turning universe records itself wherever persistence allows. Starlight stretched across billions of years arrives with a polarization pattern that preserves the orientation of ancient scattering and the slight lensing impressed by drifting structure. The map of that pattern keeps faith with early ripples so that a snapshot of the sky becomes an album of dynamics. In a laboratory, long fibers coil light around coils of glass in store phase, a domestic echo of the way distant disks store their rotation in the color and rhythm of their glow. Even empty space retains the passing of a powerful wave as a small permanent offset in the separation of free points and nonlinear memory, written not on paper or stone but on geometry itself. Planets keep books in rock and ice. Lava cools and freezes needle-sized magnets into alignment, preserving the wandering of poles and the flips of the global field. Ocean mud stacks layers that brighten and dim with shifting winds set by a turning world. Ice stores seasons as thin lines and records, far storms as faint dust, parceling each year's motion into the neat work of snow. Trees in temperate zones scribe the same alternation into wood, their cambium widening or narrowing according to the timing of light and rain that rotation and orbit deliver. A ray through a trunk becomes a history of the day's cadence as surely as a pendulum's circle becomes a history of the planet's spin. Bodies write motion in quiet currents. The heart keeps a metered spiral in muscle that twists with each beat a geometry that improves the efficiency of ejection and return. The inner ear houses delicate stones and fluid canals that report acceleration when change arrives and keep silence when the ride is smooth, a biological declaration of the difference between uniform motion and a shift. Neurons synchronize briefly into rhythms not as a choir for its own sake, but as a means to move information efficiently from one region to another. Those rhythms emerge from ions traveling along gradients and across fields in electrical weather that depends on charged particles, and on the shield a rotating core sustains. Tools extend these senses. A weight on a long wire counts the turning of the ground and turns the count into fallen pegs. A spinning wheel in a sealed casing maintains a stubborn direction and converts the difference between local and distant frames into a precession that can be measured. Ring lasers produce fringes that patrol their own basements and register the gentlest sway of the Earth's rotation. Arrays of interferometers feel the smallest change in arm length as a gravitational ripple goes by, and timing networks in space compare atomic transitions so faithfully that nanoseconds become kilometer-scale errors unless relativity is honored. Each instrument is a translator that renders motion into a trace. Galaxies are archives as well as engines. Their flat rotation curves turn invisible mass into a quantified scaffold. Their bars, rings, and warps display a script of torque and exchange. Jets from their centers point along axes set by spin and carry power into the intergalactic medium, regulating how gas cools and returns. The orientations of satellite streams around hosts whisper about the directions from which groups first fell inward, and the thickness of disks hints at a long ledger of small encounters. The present appearance of each system is a palimpsest on which many motions have been partially erased by later events and written again. The solar system holds its own palimpsest of turns and trades. The slow lengthening of the day and the moon's recession attest to a tidal transaction that conserves angular momentum by moving it outward. The obliquity of worlds, their tilts and resonances declare ancient near misses and long conversations with neighbors. Rings around giants recount shepherding by small moons and the repeated passage of density waves. Meteorites arrive with magnetic records of the protoplanetary disk, and with chemical imbalances seeded by polarized light linking present rotation to starlit nurseries. Awareness appears inside this fabric, not outside it. Brain is an organ that predicts, corrects, and remembers by arranging moving charges into patterns that persist long enough to be used. The prediction of a falling object relies on conserved momentum. The correction of a posture depends on the difference between acceleration and uniform motion. The memory of a place is stabilized by the cadence of sleep that a 24-hour world encourages. None of these acts require a special frame beyond the one the body inhabits, yet all are constrained by frames that extend outward to the horizon and inward to the nucleus. In that sense, a mind is a recorder of motion shaped by motions it does not feel, translating ancient rotation into present utility. Timekeeping is the public face of this translation. The second is defined by a specific atomic transition, a resonance in a cesium vapor cell, or in an optical lattice. The day is defined by rotation, slightly nudged by tides and tracked by careful astronomers. The year is defined by an orbit whose speed varies along an ellipse. To keep these clocks together demands constant negotiation. Leap seconds occasionally reconcile atomic regularity with planetary drift. Signals from global positioning satellites fold in corrections for speed and gravity, so that a device on a moving surface can know where it sits. Without these adjustments, maps would wander for miles each day. With them, the world's motion becomes infrastructure. There is a humility in how these memories are kept. No single archive is complete. Rocks record fields but not winds. Ice records dust but not deep ocean currents with resolution finer than the layers allow. A gravitational wave detector listens only to a narrow band and misses slower songs with periods measured in months. A telescope favors its own shade and weather. Yet when archives are compared and fitted, a wider picture forms in which motion at many scales coheres without needing a privileged reference. The agreement is not perfect. The mismatches are where attention returns, and those places often hide the next patient's reward. The story therefore does not close on a final stillness or a single answer. It settles instead on an image of a universe that writes as it moves and reads what it has written by generating systems able to compare, correct, and remember. In such a universe, rotation is both cause and record. It sculpts disks and fields, launches jets and waves, sets days and seasons, supplies polarization and torque, and leaves marks in stone, light, and timing that later minds can find. Beyond this image, there remains the open possibility that motion itself is part of what consciousness experiences at its most basic level, not as a feeling of speed, but as the security of prediction when patterns endure. Whether that suggestion stands or fades, the inscriptions are real. Instruments, archives, and living clocks quietly agree on a cosmos where nothing truly rests, and where stillness is the harmony of shared motion rather than its absence. The path has led from pendulums to horizons and back to archives in rock and ice. Ahead lies a hush, a simple night under a turning sky, where the records continue to write themselves line by line while minds drift toward sleep.